in this video, we'll go over the code for solving the inverse conduction problem using all the methods that we have seen so far. I'll also be introducing you to how to drop parity plots. And we will see the major advantage of using the normal equations approach rather than the sort of handcrafted approach that we did for solving the regression problem, linear regression problem. Okay, so I'm going to start with the standard inverse conduction problem within a slab that we looked at. So I am actually copy pasting within this. The file that you see here is what is known as an MLX file. You can see that on top of it, IMHT week 3 code .mlx. I'll be sharing with it. The NPTEL team will tell you where to sort of download this file for this week, just so that you can play with it yourself. This is what is known as a live script within MATLAB. This is the equivalent of the Jupyter notebook that you would find within a Python script, which if you are used to using Python, you would find these IPython notebooks or Jupyter notebooks. This is the MATLAB equivalent. The major advantage of it is you have these code sections which are separate, and then you can write your own notes there. Okay, something that I do for my own research or my own work is do stuff like I would, for example, if I have some handwritten notes, let's say I have some handwritten notes for this class, maybe later on within this course, I'll introduce you to this sort of mix also. You can actually take the handwritten notes, take a photograph and put it within the code. So this is useful because you can just write a code at the bottom and you have your handwritten notes here. I haven't done that, but you can see one small example of this. This is sort of a screenshot of the question that I had given you for the inverse conduction within a slab problem. I have just taken a simple screenshot that can be interspersed with code, which is here. So you can write formulae, in LaTeX format. You can see I have a LaTeX format here that lets me write the equation. So this is something that I typed by hand. This is not a screenshot, but this is also something that was typed by hand. But you can take screenshots, you can take photographs of your written code or written hand notes and just put them. Maybe you can cut paste some portions of a book for the formulae, put that there just so that you can code it a little bit more easily. I think for practical coding, using a Jupyter notebook, in case you are using Python, or a MATLAB notebook is what I would like to call it. They call it a live script. That's all of this is extremely useful. Okay, so I have this here. The description of the problem is here. The same old problem. We have 6 thermocouples within a slab and kept at 0.01, 0.02, 0.03, 0.04, 0.05, 0.06. And the temperatures are given here. And based on that, we basically wish to find out we wish to estimate the heat flux as well as the boundary temperatures. Now, as we know, this basically boils down to 3 tasks. Our tasks are basically the following. You first have to model the forward problem from the physics of the problem. Then you have to solve the inverse problem. As we saw, the solution of the inverse problem is basically finding out the parameters of the forward model. Okay, so the unknown parameters you wish to find out in a least square or in an optimal sense using linear regression. And then you post-process. You know, maybe you determine the quantities of interest using the determined parameters and the forward model. Additionally, you could also do something like, let's do this. You could additionally do things like visualize the solution. Okay, so you can have the physical plot, or you can have the parity plot, etc. Okay, so we'll do those 2 here in this. Okay, so the forward model, as you remember, how we determined the forward model was to solve the physical problem, which gave us t equal to ax plus b, or the way we took it, we called y hat as the predicted value of t, or the model for t, and we wrote that as w0 plus w1x. And basically, we want to find out the optimal values of w0 and w1, as we have been doing over the last couple of weeks. And this is given by minimizing the cost function. The cost function is the gap between the model and the actual predicted value, the actual ground truth squared. Now we used two different approaches. One was a direct formula. So the direct formula, which we determined by analytically calculating del J del W0, setting it to 0, del J del W1, setting it to 0. And we had written, if you go back to your notes, I had written two alternate expressions for this. The expression I am using right now is the most popular one, which you will see. Rather than the averages approach also, which I had told you, you basically get W0 and W1 with this formula. So I am first going to show you how the direct formula is coded in. First, of course, you have to write down the data. I hope I have written this down correctly. So 0.1 through 0.06, I wrote down x. This portion, x equal to x prime, is just a transpose. So this looks like a row, but I transformed it into a column by writing this. This prime here just represents a transpose in MATLAB. Same thing here. Data here is 15.46 through 11.42. 15.46 through 11.42 up here. And I have just given those 6 y data points. And again, y equal to y transpose. M here is the number of data points. You can see this in the formula also. M is the number of data points. MATLAB allows this. You give a vector x, it will calculate m. M would have been calculated to be 6. I will show it to you once we run the program. Okay. Sx, I have put the terminology that capital S represents sum. So Sx is basically, you can calculate sum of x. There is an internal function in MATLAB which does this. Sy is sum of y. Sx2 is obviously sum of x square. If you put a dot, it basically means every element of x is squared and gives a new matrix. So I can dot represents element wise multiplication or division, etc. You can do this, or power. You can do all those operations. So x dot square. If I do x square, it can't do x square because x is a column matrix. You can't do a column matrix versus multiplied by a column matrix because the matrix sizes won't match. So same here. You have the column matrix x, the column vector y. You can do dot star y, means x1, y1, x2, y2 would be the output. And then I take sum of that. So I have sum of xy. You can see that above there, you have sigma xy. This den is the denominator, which you can see at the bottom of both these expressions for W0 and W1. I have declared a denominator, which is m times sigma x square minus sigma x the whole square. Okay, so this is the denominator of both the expressions. The numerator of the x0 or W0 expression is sigma y multiplied by sigma x square minus sigma x multiplied by sigma xy. Similarly, the numerator of W1 is m times sigma xy minus sum of sigma x multiplied by sigma y. So these two are calculated. And at this point, I evaluate W0 as numerator 0 by denominator and W1 as numerator 1 by denominator. So we'll just run this section. And here you get a display. At the bottom, you can see 15.97, which we would have calculated even earlier, is W0. And minus 83.91 is W1. And using this, you can now calculate all the other terms, which we already did in the previous videos. For example, determining T0 can be done by doing W0 plus W1 multiplied by 0, etc., etc. Okay, so if you wish, you can find out T0 as W0 plus W1. You can just call this as X0 is 0, the location 0. And if you want T0 multiplied by X0. Similarly, X at the right end is 0.07. You can now find out TL as W0 plus W1 times XL. Okay. You can display both these values, T0 and TL. We had calculated these values earlier also. Okay. Sorry, I should have put a bracket here. So we found this out even earlier. 15.97 was the predicted temperature at the left, and 10.10 was the predicted temperature at the right. We could also find out minus k times W1, which will be minus k dt dx, etc. So all these things we have done earlier. But the more interesting thing is to calculate the same W0 and W1 in a different way, okay, which is the normal equations approach. So the normal equations approach is, remember, we just did it, x transpose x times W is equal to x transpose y. This is the equation that we got in the last couple of videos. We had derived this. And we want to set this up. Remember what X is? X is the design matrix. Okay, so if I come here and we can look at what X looks like. You can see here. I'll just write it out here. So you can see 1 and then x1, 1 and then x2, and so on and so forth. So this is just every row here is one data point with one appended at the beginning. That's what I'm doing here. A bunch of ones. How many ones? There are m ones, because m is 6, as you can see here. M is 6, and you write 6 ones and then you put an x on the next column. That's what we did. Then we can evaluate y. Y is just the right hand side. It's just the temperatures that we had given here. I should come here and I'll just run this section. I will run this section also. Okay. So when I come here, I have the LHS. LHS, remember, as we saw in the last video, should be a 2 by 2 matrix. I had calculated that the last time. So X transpose X is the LHS. Remember, prime represents transpose. So X transpose X is the LHS, and X transpose Y is the RHS, and you are now just solving a 2 by 2 system. Now this thing here, LHS is backslash. This is a way, MATLAB way of writing for inverse of LHS multiplied by RHS. Okay. But this is more efficient. So it uses internal routines like Gauss elimination, etc. So never use unless really required, even within MATLAB, especially when you have large matrices, it's inadvisable to actually use inverse of LHS. Instead, it is better to use LHS and put a backslash. Okay, put a backslash RHS. It simply means an effective way of calculating LHS multiplied by inverse of LHS multiplied by RHS. So if you do that, you see you get exactly the same results as before. See, earlier we had here 15.97 and 83.9143. Same thing here, 15.97 and minus 83.9143. You might suspect that some other digit later on might not work. So I actually calculated this. I calculated the vector W minus W is my new vector, which is the normal one, and W0, W1 were the old method. So I did this error, and the error was calculated by the norm. Remember, I had talked about the norm in the last thing. All it does is it takes the square root of the error 1 square plus error 2 square plus error 3 square, and you see that the difference is somewhere in the 13th decimal place, and this is only because of round off. Okay, machines don't calculate exactly. If you have a calculator, you can calculate it only to 6 decimal places, 8 decimal places or 10 decimal places. Similarly, this has a certain amount of accuracy, and this is called round off error. Basically, there is no difference between doing it in the normal equations approach or in the approach that we have done here. Okay, so you can see that. But I'll first show you the plots, but there is a major advantage to the normal equations approach, which I will show you. I have separated out the code in another place. But before that, let me just show you plots. Okay, so I've done that. Let's come here. So I'm going to plot the results. Okay. So if you plot the results, if you just look at the physical plot, this is the physical plot. Of course, it's blown up. It would have been a little bit smaller, or the gap would seem to be smaller in the case of the things that I showed in the slides. But this is basically the physical plot. Again, you can see the blue dots here are the experimental truth, and the red line here is the model prediction. And the red line and the model is somewhat close to the blue dots, but how close, how far is something we can't easily determine, for which you need the R square metric. So the line here is just plot. So notice this, y hat is our model prediction. I should actually change this to just so that it looks better. So yeah, so y hat is w naught plus w1x, which I have written here. This is the model prediction. And then I have plotted x versus y hat. So notice what is being plotted in a physical plot. X versus y or y hat is what is being plotted here. Now we had our R square metric to determine how good or how bad the fit is. Remember what R square was. R square was 1 minus SR by ST, where SR is the sum total residual, and ST is the sum of residuals, and ST is the total residual, basically the gap from the mean. So SR is calculated here. Y is, of course, our ground truth or experimental truth, and y hat is our model. Sum of that, again, notice the dot. This dot is there because we want to do y1 minus y hat 1 square plus y2 minus y hat 2 square, so on and so forth. Y bar is the mean value or the average value, and now you can easily calculate this as ST is y minus y bar the whole square, and R square is then 1 minus SR by ST, and you can see this value here. We had calculated it. I might have said 0.9174. Again, that is due to round off. I might have been taking just 3-4 decimal places. Anyway, you know that this is a around 0.917, and this is a pretty good fit. Okay, so R square is 0.917. Okay, now let's look at the parity plot. Okay, physical plot will show x versus y, but the parity plot, which is what we are interested in, will show y experimental versus y model. That is y ground truth versus y model. Okay, let me see if I can change this. Okay, so we also plot a 45-degree line, which is the ideal model. The ideal model would give you exactly y equal to y hat, and we want to plot that too. Okay, so the plot the reference ideal line, which is y minus y hat. This is the model points. Remember, as I said, for a parity plot, all you are plotting is y versus y hat. Okay, notice this. So now you get this here. Okay, y versus y hat. You can see the scattered plots. The blue dots here are y versus y hat. For example, as we saw earlier, here approximately our prediction. I should have put the x and y labels. Let me quickly put those here. So x label is, we have the ground truth, experimental or observed data, versus y is the model prediction. So this is what we notice here. So what we notice is there is some scatter here, which is far off from the model, from the ideal line. The red line, on the other hand, you can see here, is basically the ideal line. So this ideal line, it differs from how we are predicting, and you can see that at certain points. For example, this second blue point that you can see on your screen seems far away from the ideal line. So you might conceivably say it's an outlier. What should be thought of as an outlier and what not is something we will discuss when we come to the probability portions of this course. But as of now, it looks far away. So this is at least a point worth investigating further. And this kind of insight comes only within a parity plot. Again, if you had this in 3D, it would still look similar because we are only plotting y versus y hat here, and y always remains a single variable and y hat always still remains a single variable, even if you have three-dimensional temperature or whatever plot. Okay, so you can always draw this plot, and we will exploit this later on in the course. Okay. Now, I want to show you the advantages of using a normal equation approach. So I am going to take another code. So this code is a purely normal equations code. I have not done that W0, W1 exact expressions directly here. Okay, but let's see how we can exploit it. Okay, so it's the same code as before. So let's rerun the entire code. All I have done is remove the previous portions. You can still see the same results as before, 15.97 minus 83.91. And you have these plots here, the parity plot, R square, etc. Now, the interesting thing is this. Now, suppose I change my features back here and say, okay, I don't want just a linear model. I want a quadratic model. All I need to say is it doesn't depend only on 1 and x, but I also have an x square. The moment you have x square, the magical thing is this now. So let's come here just to show you how this works. Now, let's write x on the right hand side. So now you see it has 3 columns. The first is the constant column. You can think of it as x power 0. The next is x power 1. And the third is x power 2. So you can see it has squared the second column. Okay. Now LHS, y still remains the same. LHS has now become x transpose x. So now if I write out LHS, you will see this is now a 3 cross 3 matrix. This is just very small. Don't assume that the last element is 0. This is just a very, very small element here. So this is now a 3 cross 3 matrix. And RHS is still a 3 cross 1 matrix. And if I solve for W, this automatically recognizes that now you are going to have 3 features or 3 basically coefficients, W0, W1, and W2. And the function, as you would have seen in the previous videos, is basically W0 times x1 or W0 times 1 plus W1 times x plus W2 times x square. So it has automatically calculated these coefficients without me explicitly writing the model, because this assumes it's a linear model and that the 3 features are a constant, x, and x square. Okay, as I said, you could have made it sin x and it would have given an entirely different model. Okay, now if we come here and we plot the data, I'm going to do the whole thing now. Now notice our model prediction is a curve. Okay, so the red line here is a curve. That's because it's a quadratic curve. It kind of seems to fit better, but we put no extra effort as far as the formulation of the problem is concerned. This is the power of the normal equations approach. We really did not recalculate the coefficients. We just calculated all the expressions one shot. You can see that it kind of fits better. However, we know that this is not the physics of the problem. Later on, towards the fag end of the course, when we come to neural networks, we will discuss this in greater detail. How to determine models when we don't know the underlying physics of the problem. But you can see that the experimental truth is a little bit farther away, but you can see the curve for the model prediction. R square is higher, 0.96. I make a parity plot. Notice this, the parity plot does not show a curve because what we are comparing with is just a straight line. Okay, we are just comparing with the line that y equal to y hat, whereas there is some amount of variance and this seems genuinely lesser than before. Okay, but that doesn't mean this is necessarily a better model. The model was, the experimental data points were generated from a linear fit. But just because something looks better doesn't mean it's more physical, but this would fit the data better right now. Okay. Now, if we go back and by chance, I add an extra feature, x cube, I can do that too. Okay. If I do that, Now let's look at LHS. LHS is now a 4 by 4. Again, these are not zeros. These zeros which appear here are just some very small numbers. So I am just going to continue here. Now notice I have 4 predictions: W0 plus W1x1 plus W1x plus W2x square plus W3x cube. So we have 4 sets of coefficients, and again a curve here. R square is approximately the same, so this is not necessarily a better fit. And you can also see a parity plot, which gives you maybe again some points are better predicted, some points are not so better predicted. But the advantage that I want to emphasize is that you can actually put anything here, okay, any so-called non-linear feature here. The map is always linear in the W's, okay, and it is automatically calculated using this normal equations approach. For example, I don't know how well this will perform, but just for the sake of argument, let us say we put e power x. So this model will be W0 plus W1x plus W2 e power x. What is the best fit? Let's just run it and check. This doesn't look too bad, actually, if you look at it. Okay, so this one looks a little bit better. We can also try sine x or cosine x or something of that sort. So some amount of curvature. Okay. Let me just clear the whole thing up and then redo the run. And you can see, I mean, sine has captured some little bit of it. Now, a couple of things I want to emphasize here is that the normal equations approach is easily generalizable. Okay, so if you are doing assignments, I would recommend that you write a normal equation approach, or at least you can copy the code that I have, and you can do several assignments using this. The second thing is, notice that it is irrelevant what we put in the model here. This simply says what that coefficient multiplies with. So basically, you are going to get W0 plus W1 times x plus W2 times sine x is the model. So nothing stops us. The terms that we cannot have are terms like sine of W2 or W1, W2. Those terms we can't have. This is basically linear in W, can be nonlinear in X. Okay, so please remember what linearity means. In the next video, we'll look at a couple of other variants of linear regression. All of them fall roughly within the same framework. We will also look at weighted linear regression, which changes the normal equations a little bit, but we'll see all that in the next video. Thank you.